It's a huge pleasure for me to be here. My very first meeting at all, I think, was here. And I remember going on long hikes through the trails here and talking to Artem about generic automorphisms when I was a master's student in Paris. So yeah, we even shared a room because Martin Hills wanted us to talk, and we did, and that was very useful. Thank you, Martin. Also, I'm really pleased to be here to celebrate Frank and his contributions to model theory. I mean, Frank started helping me before I even met him because I learned so much from reading his Simple Theories book. And then, when I was a postdoc in Paris, I spent several very intense hours in Frank's office trying to figure out what anisopy-1 group theory ought to be. And I feel pretty confident that all of the positive theorems we know about anisopy-1 groups we figured out together. Unfortunately, there aren't any positive theorems that we know about anisopy-1 groups. There was on a brief, for a brief period on Frank's website under works in progress, there was a paper called anisopy-1 group theory with me and him as the author, and then at some point that disappeared. But hopefully we'll find reason to revive that project. So the plan for the day is to talk about this project, a Borovik-Cherlin bound for primitive pseudo-finite permutation groups. And there's a lot of group theoretic detail, so I'm going to try and give a very high-level overview of what's going on in these arguments rather than getting too bogged down in the details. So the project is joint work with Ulla, and as I was writing the talk, I had occasion to glance at Simon Thomas's thesis. And somewhere in the introduction, he's talking about how if you're an algebraist trying to read the thesis, it's going to be very easy for you because I've summarized all the model theory you need in 5 pages. On the other hand, if you're a model theorist trying to read the group theory, you're on your own because I would have to summarize the first 13 chapters of Carter's simple groups of Lie type, and I'm not going to do that. So I remember reading that and thinking, gosh, there must be a more efficient way of learning group theory than just slogging through Carter's Lie group, simple groups of Lie type. And in fact, there was. I mean, I invited Ulla to visit, and basically we thought about Chevalier groups in an intense way for 2 weeks, and this project kind of emerged. So the basic object of study is a permutation group. So what is a permutation group? It's just a set X with an action of a group G, and we'll assume it's faithful. So it's the same thing as an injection of G into the symmetries of X. And okay, most of you have seen these definitions before, but it's worth just having them in front of us. So a permutation group is called transitive if it has only one orbit, which means that you can get from one point of X to any other point in X by moving by an element of the group. And it's called two-transitive if you can move pairs to one another. So if I give you an action of G on X, then you have an induced action of G on pairs of X, where you apply the action to each coordinate. Now, of course, that can't have just one orbit because you have the diagonal, and you can't take an element to the diagonal to a distinct pair. But if you forget about the diagonal, then what it means to be two-transitive is you can move any pair of distinct elements to any other pair of distinct elements. And a permutation group is called primitive if there's no non-trivial equivalence relation on X which is preserved under the action of the group. And I claim that two-transitivity implies primitivity implies transitive. As I'm standing here, I'm realizing I should say that X should have at least 3 elements. Otherwise, maybe this isn't true. So what does it mean to be a trivial equivalence relation? That means that you have at least one equivalence class that has 2 elements in it, and you have at least 2 classes. Okay? So the trivial, sorry, that's non-trivial. The trivial ones are everything is equivalent or only equal things are equivalent. Those are the 2. So if you're two-transitive and you have at least 3 elements, then of course there's going to be something that takes an equivalent pair to an inequivalent pair. So that meant that any equivalence relation that you write down can't be any non-trivial equivalence relation that you write down can't be invariant of the action of the group. Okay, so two-transitive implies primitive implies transitive. All right, this is going to be the basic object. So permutation groups are everywhere. All of mathematics basically is about group actions, and primitive permutation groups form sort of the building blocks. The idea is if I give you a permutation group and there's some invariant equivalence relation, then of course I can look at the induced action on an equivalence class and the induced action on the set of classes. And that gives me a way of representing this in terms of what's called the Reith product. So I can sort of analyze this more complicated permutation group into the action on the class and the action on the classes. And if I do this analysis enough, then eventually I'll arrive at the primitive building blocks. So in the same way that if we want to study group theoretic questions, often we can reduce to simple. When we want to study permutation groups, often we can reduce to primitive. And there are several ways that you can understand what it means to be primitive. Okay, one of them is the definition about preservation of equivalence relations, but another one is in terms of maximality of point stabilizers. So if I give you a transitive permutation group, then that permutation group is going to be primitive if and only if each or all point stabilizers are maximal. So if you're transitive, then all the point stabilizers are conjugate to one another. So if one is maximal, then they're all going to be maximal. And the maximality of this is equivalent to the primitivity of the permutation group. And one way of seeing that is if you have a transitive permutation group, then you can think about the set on which you're acting as really just being the left cosets of the point stabilizer. And if you have an intermediate group, which is bigger than the point stabilizer but smaller than the group, then you have an equivalence relation that says one coset is equivalent to another if they're equal to the same coset of that larger group. And that's a non-trivial equivalence relation, which is G invariant. All right, but then this is going to be sort of significant for what comes later. There's a kind of striking characterization of permutivity due to Higman, where if I give you a permutation group, then you get an induced action on two-element subsets. So x choose 2 is going to be my notation for the two-element subsets of x. And if I take an orbit, what is that orbit? It's a set of two-element subsets. I can think about that as a graph relation on x. So each orbit under the induced action on two-element subsets gives me a different way of putting a graph on x. And what you'll notice is that, okay, because it's an orbit, that's a G invariant edge relation. So the group is acting as automorphisms of that graph. And what Higman proved is that the action of G on x is primitive if and only if each of those graphs is connected. And it's not so difficult to see why. So if I give you an orbital graph which is disconnected, then the equivalence relation of being in the same connected component with respect to that graph is a G invariant equivalence relation. So if you're disconnected, then you can't be primitive. On the other hand, if you are not primitive and you take some invariant equivalence relation, then you can look at the orbital graph associated to an equivalent pair. And you can see that that will never take you to something in a different, you can never connect from a vertex in that class to something which is in a different class. So it's not a difficult thing at all, but it gives you a different way of thinking about primitivity, which is going to be significant for what comes later. All right, so the way that we often try to understand finite permutation groups is in terms of a theorem called the Onan-Scott theorem. And the Onan-Scott theorem is significant because it gives you a kind of coarse classification of finite permutation groups in terms of something called the socle of G. And the socle of G is always a finite product of isomorphic finite simple groups. And so using the classification of finite simple groups, you can get a kind of rough description of all the possibilities for finite permutation groups. So soc G is going to be my notation for that socle, and that's the subgroup of G which is generated by all the minimal non-trivial normal subgroups. Okay, and what the Onan-Scott theorem does is it sort of gives you a case division of the different kinds. So one situation that could happen is you have an abelian socle. So I told you that the socle is always a product of isomorphic finite simple groups. What abelian finite simple groups do you know? Well, it's got to be Z mod PZ, so for some prime. So if you have a abelian socle, then the abelian socle itself is an elementary abelian P group of some size. And so you can think about that as a vector space over the field FP. And what the Onan-Scott theorem says is, okay, if you're in the abelian Sockle case, then X, the set on which you're acting, can be identified with some finite dimensional FP vector space. Now, G itself is going to be a semi-direct product of V acting on itself, and H, which is going to be a subgroup of sort of GL and P, and that's going to be the stabilizer of 0. So this is what we call an affine permutation group. You have V, which is acting on itself, and then you have some subgroup of GLN, and then you look at the semi-direct product, and that's acting on V in a primitive way. So this is the affine situation. And then there is the situation where the Sockle is non-abelian. So here we have the Sockle is going to be T to the K for some non-abelian simple group T, and we have some situation. So the following situations are possible. So one is that it's not really a product. The Sockle is actually just a finite simple group, and then G is almost simple, which means that T is a subgroup of G, which is a subgroup of the automorphisms of T. Now, in this situation, I haven't said how it acts, so I can say a bit more later, but at least in this case, we know what the group looks like. Another situation is what's called diagonal action. So here, X is identified with the diagonal copy of T and T to the K. So I just look at coordinates which are all the same, living in T to the K. That's a copy of T living inside of T to the K. And G will act on the cosets inside T to the K. And then you have something called the product action. And this is sort of the hardest one to see. So the product action, you have K's at least 2. There's a primitive permutation group HY in the almost simple case, say. And you have some transitive subgroup of S to the K, permutation on K elements. And G is going to be the Reith product of H and K, where H to the K semi-direct product P is acting primitively on Y to the K. Okay, if you haven't thought about this before, then it's really hard to get a picture of what's going on. Yes? Well, the almost simple case says G is almost simple. So G, what does it mean to be almost simple? It means that you are sandwiched between a simple group and its automorphism group. Yes, G is almost simple. That's the situation. So I haven't said anything in this case about what it's acting on. But okay, what it's acting on is cosets of some maximal subgroup. Okay, that's not very informative, but we can say more later. Okay, so for the product action case, if you want just like a mental model of what this is looking like, then you can take K to be 2 and take H to be S5 acting on a 5-element set. So S5 is almost simple because it is the automorphism group of A5, which is a simple group. So S5 acting on a 5-element set, think about now, so Y is going to be our 5-element set. Think about Y squared as a 5 by 5 grid. So one copy of S5 acts by permuting the columns, and one copy of S5 acts by permuting the rows. And neither of those is primitive, of course, because you have the equivalence relation of being in the same column, or the equivalence relation of being in the same row. But you can also have an action of S2, which swaps along, which reflects along the main diagonal. And that gives you a semi-direct product where you're looking at S5 times S5, semi-direct product S2, which swaps the coordinates. And that is primitive. And it's an example of this kind of product action. So if you've never seen this before, then you can think about that case as a sort of enlightening example. But I mean, it's also maybe not so enlightening. Okay, so anyway, the Onan-Scott theorem says this is what finite primitive permutation groups look like. And the cool thing is that you sort of have the classification of finite simple groups around to sort of narrow down the possibilities. All right, so we are really interested in definable primitivity in pseudo-finite settings. So suppose that Gx is not just an abstract permutation group, but it's definable in some theory. So what that means is that the group is definable, the set is definable, and the action is definable. So this is all in some definable, it's in some model theoretic context. So we say that Gx is definably primitive if there's no non-trivial definable G invariant equivalence relation on X. And in the same way as before, we said that primitivity is equivalent to maximality of the point stabilizers. If I give you a transitive definable permutation group, it's definably primitive if and only if each point stabilizer is definably maximal. So you can't find a supergroup which is definable sandwiched between the point stabilizer and in the group, strictly. Okay, now it's obvious that, that definable primitivity is a sort of weakening of the condition of primitivity. If you have no, well, yeah, it's a weakening in the sense that you can be not primitive and definably primitive. So if you have no G-invariant equivalence relation at all, then of course you don't have any definable ones. So this is the sort of setting, and the sort of motivation for all of this comes from this sort of theorem of Borovik-Cherlin that tells you that in a finite Morley rank setting, the behavior of definably primitive permutation groups of finite Morley rank is really constrained. So what this theorem says is, okay, explicitly it says there's a function from natural numbers to natural numbers such that if Gx is a definably primitive permutation group of finite Morley rank, then you can bound the rank of the group by f applied to the rank of x. So what it's saying is sort of uniformly, you can always determine how big the rank of G is in terms of the rank in which it's acting, or the rank of the set in which it's acting, before you know anything about the theory. So this is maybe familiar to people from the rank 1 setting. So there's a theorem of Rashofsky which says that in rank 1, so acting on strongly minimal sets, say, there are really only 3 possibilities for what the group can look like. It can look like sort of a vector space acting on itself, in which case it's rank 1, or it can look like an affine group acting on the additive group of a field, in which case it's rank 2, or it can look like PGL2, or yeah, PGL2 acting on affine line, in which case it's, or the projective line, in which case it's rank 3, and that's it. So acting, so in that case, if the rank is 1, then the group is rank at most 3. Okay, so in general, you're not going to get such a nice description of what the groups can look like, but you can still prove that they're highly constrained in the sense that the dimension can't grow arbitrarily. Now the proof itself relies on an analog of the Onan-Scott theorem, which is due to Dugald, McPherson, and Anand-Pillay. And in the Borovik-Cherlin paper, they also use a bunch of results of Frank on fields of finite Morley rank, so-called existence of good tori. Yeah, so this was sort of a long and hard paper, and it was very influential. And it led to an interest in proving analogs in other tame settings. And one of those is the setting of pseudo-finite groups of SU rank, finite SU rank. So on the one hand, going from finite Morley rank to finite SU rank means that your rank notion is much less well-behaved. But if you additionally insist on the groups being pseudo-finite, then the classification of finite simple groups is available to you. So in the finite Morley rank case, the rank satisfies everything you could possibly ask for, but you don't have a classification of the simple groups. You have a conjectural classification of the simple groups, the Cherlin-Zilbert conjecture, which sort of gives you an idea of what you should expect, but of course you have sort of fewer explicit classifications. On the other hand, here we have an explicit classification that's as good as we could ever hope for, but the rank is less well behaved. And then the idea is, if in that situation of the trade-off, could we still get something nice? So the question that we want to think about is this one asked by Elwes, Jaligo, McPherson, and Wrighton, which is, can you prove the same kind of theorem? So considering a definably primitive permutation group, which is pseudo-finite and of finite SU rank, can you bound the rank of the group in terms of the rank of the set on which it's acting? Okay. And the theorem is that you can. Okay. So yes, you can. And all right. So the proof it involves some steps that are a little harder to summarize than I would have liked. So I'm going to try and just give a sort of flavor of the ingredients without going into too much detail. So there were some precursors to this, mostly by Elwes, Jaligo, McPherson, and Wrighton. So they were studying primitive pseudo-finite permutation groups in a finite SU rank theory with this sort of additional assumption that in the theory, TEQ eliminates exist infinity. So this turns out not to be so important. So what they proved is that in the SU rank 1 setting, you have you have an analog of Reshevsky's theorem on strongly minimal sets. So in this situation, if you're acting on a set of rank 1, well, then you either look like an elementary abelian P group or a torsion-free divisible abelian group acting regularly on itself, in which case the rank of the group is 1. Or you have an interpretable pseudo-finite field around, and you look like the affine group acting on the additive group of that field. Or you, or X is the projective line, and you look like PGL2. So, okay, and then there's this kind of subtlety, which is you could be sandwiched between PGL2 and P gamma L2, which is the extension by field automorphisms of that group. All right, and Tingshan proved a generalization of this theorem where you weaken SU rank to the setting of finite dimensional groups, satisfying a certain chain condition on centralizers and stabilizers. Okay, so that's just in the rank 1 setting. And then in general, Ellis, Jaligo, McPherson, Wrighton proved the theorem we wanted, but more or less, but for pseudo-finite dimension. So what they proved is that in their setting, so again, with all the assumptions, so you have Gx is a finite SU rank, it's a primitive pseudo-finite permutation group in a finite SU rank theory, eliminating existinfinity, then if you write the group as an ultra product of finite permutation groups, then you can find some constant, C, such that the cardinality of Gi is bounded above by the cardinality of xi raised to the C. So for those of you that are accustomed to thinking about pseudo-finite dimension, what this is saying is that Gi is bounded above by a constant multiple of xi to the, probably it does. So I'm not sure about how uniform this is, because that's part of the question, I think. So yeah, I think probably it does. So, but it's not so obvious how much it depends. So I think they ask as a question at the end. They're like, well, maybe Dougal is the one to answer this question. But yeah, this was based on these results of Cameron and Latsipabai. And they mentioned at the end of the paper where they proved this that it's not obvious how much it depends on the Lie rank of the group. So I think maybe it does depend. Okay. All right. So I want to say a bit now about the various tools that we use. And okay, one of them are just some basic properties of SU rank, which I haven't really said anything about. So for us, finite SU rank implies that you're in a simple theory, and SU rank is defined in terms of forking. And if you haven't thought about that before, it's not going to be enlightening to see it now. But the basic thing is that SU rank, more or less, it drops whenever you pass to something infinite index. So if H contained in G is a definable subgroup, then the index of H and G is finite if and only if the SU rank is the same. So one of the big differences between working in sort of a finite Morley rank setting and a finite SU rank setting is that unlike the Morley rank setting, you don't really have a sensible notion of multiplicity. So in the finite Morley rank setting, if you read papers in groups of finite Morley rank, there's this sort of ubiquitous move of passing to connected components. And here you just can't do that. So you have to, think about almost stuff instead. But at least for this particular issue, you at least know the rank will drop when you pass to something infinite index. And then you have a kind of additivity as well. So if H is a definable subgroup of G, then the SU rank of H plus the SU rank of the quotient is equal to the SU rank of G. And then also there's an analog of Zilber's indecomposability theorem, and then from that you can get as a corollary that if I give you a non-abelian definably simple group, meaning it doesn't have any definable non-trivial normal subgroups, then actually it doesn't have any non-trivial normal subgroups at all. So definable simplicity implies simplicity. Okay, so these things are sort of in the background. All right, so what we would like to do is we would like to say, in analogy to the fact that definably simple coincides with simple, we would love to say that definable primitivity coincides with primitivity. That would be very nice. It's also false. So I'm going to give you an example, which is an adaptation from an example given in the finite Morley context by McPherson and Pillay, just to give you a flavor of how these things go. So let G be your favorite finite group. I don't know, let's think I don't know, like SL2 6, okay? Or SL, wait, that 6 is not prime. SL2 19. Okay, so take your favorite finite group, and let I denote an infinite set of primes, such that for some d, and for each prime in that set, there is an irreducible representation Vp of G, where Vp is a d-dimensional vector space over Fp. Okay, so if you're like me and you don't know anything about representation theory in characteristic P, there's a cheap way of producing such things. So Maschke's theorem says that if I give you a representation of the group G and a prime, which is over a field whose characteristic does not divide the order of the group, then it decomposes into irreducibles. Okay, so every group G will act on an FP vector space, of dimension cardinality of G via the regular action. You just have a basis element for every index, for every element of the group, and then you act by permuting the subscripts. And so take an irreducible, which is of dimension less, take one of the irreducibles, and by pigeonhole, you can assume that they're all of the same dimension. So, it's easy to arrange this situation. All right, now, irreducibility of the action will entail that the permutation group, Vp semi-direct product G, Vp is primitive. Okay, let's think about why. So what do you have to prove? You have to prove that point stabilizers are maximal. So what is the point stabilizer of 0? Well, the point stabilizer of 0 inside Vp is just the group G. Because Vp acts by translation, and certainly 0 is the only element that takes 0 to itself is 0. So the pointwise stabilizer of 0 inside Vp is G. So if I take a larger group, a supergroup of that, it's got to contain some element of Vp. So I have 0 times G is like my point stabilizer, and if I add some non-zero element of Vp, well then the group that generates will be closed under the action of G, and therefore has to be all of Vp by irreducibility. So that says exactly that G, as the point stabilizer of 0, is maximal, so this group is primitive. So then we take an ultraproduct. So GV is going to be a non-principal ultraproduct of these situations, and then F is going to be the associated pseudo-finite field that we get by sending Fp to F. Then if you look at this permutation group, V, semi-direct product G, and V, it's interpretable in F because the dimension is fixed, right? So basically this group G is acting by matrices on some finite dimensional vector space over F. That's certainly something you can write down in the theory. And F as a pure pseudo-finite field is rank 1. So certainly this situation is a pseudo-finite permutation group of a finite SU rank. And as an ultraproduct of primitive permutation group, it's definably primitive. Because if you had a definable invariant equivalence relation, then just by Wash's theorem, you could pull that back to the factors. But it's an infinite ultraproduct. So the cardinality of V is continuum. It's of size continuum. And G is finite. So there's certainly some countable G invariant subgroup U of V. How do you do it? Well, you just take any non-zero vector in V, and then you close into the action of G, and then you look at the group that it generates. And that's a subgroup. It's not a subspace, right? And that's the key distinction, ultimately. So you get some subgroup U, which is contained in V. And then the stabilizer of 0 is G, as we argued before. That's strictly contained in the semi-direct product of U acting on G, which makes sense because U is G invariant. And this is countable, and V is of size continuum, so that's properly contained in V semi-direct product G. So that says that the point stabilizer is not maximal, so the action is not primitive. So this is a bit of a bummer. It says that definable primitivity and primitivity are not the same. All right, that's the proof, by the way. No, because the action of G is still irreducible. So the thing is, irreducibility is something you can write a sentence that expresses. So certainly there's not going to be any G invariant subspace, but there can be G invariant subgroups, and that's the difference. And this is really, so why do I want these over FP? Well, in the FP situation, it's really easy to see what's going on because it's the prime subfield, so group generated by and span are the same. There's really no difference. But as p goes to infinity, then you see a difference between these two things. Yeah. All right. But definable primitivity equals primitivity almost. Okay, so the thing that made this thing work was that the point stabilizer of 0 was a finite group. And that turns out to be equivalent to the kind of problem. So, so what Ula and I proved is the following thing. So suppose Gx is a definably primitive permutation group of finite SU rank, then Gx is primitive if and only if the point stabilizer is infinite for some all x. So one direction of this, the direction that says if Gx is infinite, then Gx is primitive, was basically known, I think. I mean, so it was known under some additional assumptions. So Elwes, Jaligo, McPherson, Wrighton proved that if you assume SU rank of G is bigger than the SU rank of X, and the ambient theory T eliminates exist infinity and TEQ, blah, 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 then it's primitive. And Elwes and Wrighton earlier proved this for Gx in a measurable theory. Okay, so it was close to known already. And our proof is really something that, I don't know, we learned how to do by reading things written by Frank. So the idea is to establish primitivity, we first reduced to showing that the almost normalizer of G is Gx. So what does it mean to be a normal subgroup? What it means to be normal is that if I take a conjugate of the group, then it's of index 1. Then its intersection with the group is of index 1 in the group, right? So H is normal in G if and only if H to the G intersect G has index 1 in the group, which is a sort of silly way of saying it. But what it means to be sort of in the almost normalizer is that if I conjugate H by G, so I look at H to the G intersect H, that it's a finite index in H. So the almost normalizer collects all those things that sort of that are there, and if the amount of commensurability, like if that index is finite, then you can get uniformly, then you can get a definable group. And so we reduced to showing that if there's any bigger group at all, then the almost normalizer will grow. So we have to prove this, and then the way that we prove this is by using Schlichting's theorem. And I don't know, every time I go to a talk where someone invokes Schlichting's theorem, someone else says, oh, that's Frank's favorite theorem. So I don't know, I mean, it's a very Wagnerian technique. So cool. And then what's nice is that we can also go the other direction. And Ula found this theorem of Smith, which is not so old actually. It says if Gx is primitive and X is infinite, and Gx is finite, then the group G must be finitely generated. So already that shows you that an ultra product can't have this property. But actually using some theorems of Ould-Hussein and Point, we were able to prove that actually, okay, you just can't have this situation at all. So if G is finitely generated in this setting, then it's got to be finite. Cool. Okay, so we at least know that as long as the point stabilizer is infinite, then we can assume that the action is primitive. So notice that if Gx is definably primitive pseudo-finite of finite SU rank, then either Gx is outright primitive or Gx is finite. That's what the theorem said. And if Gx is finite, then since X may be definably identified with G mod Gx, because the action is transitive, we have SU rank G equals SU rank G mod Gx, which is SU rank of X. And of course, then we have a bound. Then they're equal, in fact. So we might as well assume that we have an outright primitive action, because otherwise we're in a case that we know how to handle. All right. So the reduction then is to the case where we're primitive, and now we need an understanding of when we have an ultra product of finite permutation groups, which is itself primitive. And this was done by Liebeck, McPherson, and Tent. So Higman's criterion said that if I give you a permutation group, then it's going to be primitive if and only if the orbital graphs are connected. But if you take an ultra product of connected graphs, of course, you don't always get a connected graph. What you need to have that is that the diameter is bounded, right? Because so the diameter of a graph is the maximal length of a shortest path in the graph, right? And if the maximal length of a shortest path is going longer and longer and longer, then in an ultra product you get infinite length, and then you have a disconnected graph. So if we want the ultra product of permutation groups to be sort of primitive in the limit, then we need to know that we have a uniform bound on the diameter of the orbital graphs inside that family. And so what this paper of Liebeck, McPherson, Tent did was to classify what those possibilities are. All right, so the LMT classification, I mean, it's a coarse classification, and basically that paper has like a wealth of information about all the possibilities. And if you really want to use it, then you kind of have to like go into the classification. So I can sort of just give a rough sense of what it's saying, and there's a lot of detail on this slide, so just bear with me. So suppose I give you an ultra product of finite primitive permutation groups, then it's got to be one of the following. So, okay, one situation is you take an affine permutation, a family of affine permutation groups. So here, I've got, some vector space of dimension d for d fixed. So in my family, the dimension is fixed, but the q is going to infinity, and h is going to be some irreducible subgroup of GLDQ. So h depends on q as well, and then in the limit, I get some vector space with an action of a group on it, which is sitting in the affine situation. This is one possibility. Another possibility is I take a non-principal ultra product of almost simple groups for SI simple of fixed Lie type and GI acting in standard T action. So this is something I have not defined. And basically the idea is it's just saying it's acting on a geometric space in a normal way. So for example, it could be acting on T-dimensional subspaces of a fixed vector space. And to go into real detail, I should talk about the various possibilities for the different classical groups here, because it sort of depends. Like in the orthogonal, you have a certain situation, whatever. But anyway, it's saying it's a nice, comprehensible geometric action. Another situation is you have an ultra product of diagonal type, where the socle of the group is some finite product of infinite non-abelian simple pseudo-finite groups. You can have an ultra product of permutation groups in the product action situation. And then the really key thing is that you have 1, 2, 3, 4, and then you have situations that involve limits of groups of unbounded Lie rank. So, for example, you could imagine you're looking at PSL in Q as n goes to infinity, something like that. So if you're in that situation, then you get something which is harder to handle. But the good news is that we don't have to, because the fact that we're working in a finite SU rank theory tells us that this situation where the Lie rank goes to infinity basically can be excluded. And for those of you that sort of know what kinds of math I tend to do, might be surprised that I'm thinking so hard about particular groups. But really, for me, the motivation for doing this project at all was reading this LMT paper early on in grad school. And at the end of that paper, there's a paragraph where they said, we sort of hoped there would be a greater connection to this classification to model theory. But if you look at the situations where the Lie rank goes to infinity, or you look at, say, ultra products of ANs as n goes to infinity, these give you completely wild theories. And there are really two ways of dealing with that if you want to find a model theoretic treatment of what this LMT classification is telling you. And one of those ways of thinking about it is to, by fiat, just insist that you're only going to be interested in the ones that have finite SU rank, and ask what you get when you restrict that classification to that context. That's what we're doing here. But a totally different situation is you can think about G as acting as an automorphisms of some structure on X. And in this situation, the idea is that this classification should be a kind of analog of the Cantor-Liebeck-McPherson classification of primitive smoothly approximable structures. And this could be a kind of class of structures which look very much like the Granger example, which we know to be a kind of nice NSOP1 theory. So there are precise conjectures about how to think about the LMT classification as giving you a stock of interesting examples of NSOP1 theories that could serve as building blocks for a kind of generalized theory of smoothly approximable NSOP1 structures. So hopefully we'll talk about that, but that might have to wait till Frank's 70th. So the first approach is going to be to just insist on looking at the finite SU rank situation. And here we know that the LMT classification tells us that we can restrict attention to, I don't know, items 1 through 4 on the previous list. because we can eliminate the finite SU rank situation. And we can also rule out situations where we have infinite field automorphisms. So if you have a Chevalier group, then there are exactly 4 kinds of automorphisms of that Chevalier group. You have the inner automorphisms that come from the group. Then you have the diagonal automorphisms that come from sort of, I don't know, scalar multiplication by diagonal matrices on the Chevalier basis. You have graph automorphisms that come from the Dynkin diagram, and then you have field automorphisms. But it's a theorem of Tingchan's that if you have a group acting on a field in a super simple context, then that group has to be finite. So I mean, if you have the group as a permutation group. So we can sort of restrict attention to situations where the Lie rank is fixed, and any field automorphisms involved are only finitely many. And that's a really strong restriction. And then the basic idea from a high level is just to find fields. So the thing that we want to do is, in order to relate the rank of the group to the rank of the set, the way that we would really like to think about that is we'd like to find some field and then identify X with something that we build out of the field. So if X, for example, is a vector space of dimension D, then I can identify X with F to the D, and then I know that whatever the SU rank of F is, the SU rank of X will be D times that SU rank. So if we can do that, then if we can calculate the SU rank of X and the SU rank of G in terms of the SU rank of F, then we can bound the SU rank of G in terms of the SU rank of X by finding a formula for the SU rank of F in terms of the SU rank of X. Okay, now the reason I'm writing SU rank F is because we don't know that it's pure, right? We don't really know anything about the ambient theory. If it was a pure pseudo-finite field, it would be rank 1, and this would be much easier, but a priori we don't know anything about the SU rank of that. Okay, and there are really 2 tools that we use to understand where these fields come from. So one of them is sort of the affine situation, and the other one is the simple non-abelian Sockle situation. So in the abelian Sockle case, we have sort of a group which is acting on an abelian group, and we want to understand how that comes from an object of linear algebra. So here's the theorem, which is, I mean, this doesn't exist in the literature as such, but it's very close to things that exist in literature, and it's sort of an adaptation of something we found in the Borovik-Cherlin book. So this version of the field interpretation sort of identifies A as a linear space. So suppose I give you S, which is a semi-direct product of A and G, which is a pseudo-finite supersimple group of finite SU rank, where G is definable, A is self-centralizing in S, and it's an infinite abelian subgroup of G with no definable G invariant subgroups. There's a lot of assumptions. But in your head, you should imagine A is like a vector space, and G is like a subset of GL or GL of that vector space, and we want to identify the vector space. So if G has an infinite definable abelian normal subgroup H, then there is an interpretable pseudo-finite field F and a finite index subgroup G0 of G, so that A is a d-dimensional F vector space and G0 is contained in GLF. So it sort of says, like, if you can pile on enough group theoretic hypotheses that you know that your situation looks kind of like a vector space, then it really has to be a vector space over some pseudo-finite field. So in the affine case, this tells you how to identify from the group theoretic structure the linear structure coming from a pseudo-finite field. And then in the situation where you have non-abelian simple pseudo-finite groups, we understand what those look like by Wilson's theorem. So Wilson proved that any infinite non-abelian simple pseudo-finite group is a possibly twisted Chevalier group over a pseudo-finite field. And then Reitan proved in his thesis that the class of Chevalier groups of a fixed Lie type over finite fields is sort of uniformly bi-interpretable with finite fields. And in the case of like the Suzuki and the Ryu groups, you maybe need to have the difference field structure. But basically this tells you that, regardless of what the Sockle looks like, if the Sockle is abelian, then you can often identify linear structure over some interpretable pseudo-finite field. In the case where the Sockle is non-abelian, then it's going to be built out of simple pseudo-finite groups. Therefore, there has to be pseudo-finite field around, such that it's like the pseudo-finite field points of some simple Chevalier group. And so we have fields, and we understand very explicitly how those groups are constructed from them. And so putting that together, and again, there's a lot of work that goes into making this work precisely. But putting this together, you can compute the SU rank of F in terms of the SU rank of X, and then you can compute the rank of G in terms of the SU rank of F, and then that gives you the kind of bound that you want. All right, and so you know what's coming next. So happy birthday, Frank. Thank you very much.
I see there is a question. No? Oh, no, no. So are there questions? There is many questions. Okay, let's start with... you have to speak into that.
Well, thanks for that very nice talk. I have two questions. Well, one remark and one question.
Okay.
It seems to me that you don't really need super simple, sort of finite dimensional should be enough.
Yeah, that's right.
And secondly, I mean, there are two ways to use pseudo-finite. Sort of the strong way is to use the classification theory, and the weak way is not to use the classification theory, classification of finite simple groups.
Right.
But I guess this is very much the strong use.
Yeah. No, absolutely. So,
but yeah, given that the Borovik-Cherlin don't use it, do you think there could be a way to do this without classification of finite simple groups?
yeah, we haven't tried. But obviously, this is a question of great interest. So maybe in the background, one thing to say is that one of the reasons people are increasingly interested in permutation groups of finite Morley rank, right, is that they arise as binding groups in certain geometric situations. So you have this stuff like Jim Freitag and Rahim Musa thinking about, binding groups in DCF0 and extracting applications from this kind of thing. I mean, there are many people doing such things, but and Remy, of course. But we also have, for example, analogs of the binding group for quantifier-free internal sets in ACFA. And there you don't necessarily know that you have pseudo-finite fields around. I mean, of course you have pseudo-finite fields around, but not every group is going to be like the pseudo-finite field points of some algebraic group. And so, having tools that don't require the classification of finite simple groups would be really nice if we want to use such bounds for like applications in the same way. And I have no idea how that would look because this proof really uses the Liebeck-McPherson tent classification, which itself really uses the classification of finite simple groups. But I think it's a really nice question, and I would love to do that. And yeah, I should say that the work is very much in progress. We have kind of like a half-written preprint, and we do as much as we can in the finite dimensional case. And it's not obvious that the theorem isn't just true outright in the finite dimensional case, but we haven't really checked it, so that's why I didn't claim it. But much of the paper will be written in that way, if not all.
So I have a question. So, like in both cases, so the like pseudo-finite field is interpreted. And it has SU rank 1, right?
Well, the thing is that we don't know anything about the ambient theory. So, as a pure field, of course, it has SU rank 1, but I mean, maybe it has some additional structure that the theory imposes.
Okay. But I also think like, so there's like Dougal and other people's result of like counting the size. And I think you can like actually see how this power is related to the SU rank.
Okay. So, but do we know that if you have a...
No, I think in general, if you have like a super simple as finite SU rank and pseudo-finite, then the really? Fine counting dimension is related to the to the SU rank, yeah. I think it's even fine dimension. In this case, I think it's even fine dimension, so it's like even better pseudo-finite dimension.
Okay. Cool.
Is there any other question? Well, if not, I think we can thank Nick again for and